This is Team 4, Analysis and Redesign of an Office Chair. We chose a chair with the general features of adjustable height, stability, comfort, and mobility. Our motivations for choosing such a chair are shifting work styles to favor at-home work and steady demand for chairs across the world. Customer groups include career at-home workers and public offices. The important details we'd like to highlight in our chair assembly shown in the right are that the legs are welded, we have a pneumatic pressure adjuster. For height, we use M4 screws to hold everything together, and we use caster wheels for mobility. The primary customer group, career workers, are expected to want high-quality product for daily use comfort while being mobile across the room. For the secondary customer group, we expect that they do not care so much about comfort or whether or not the chair is stationary, and they would also prefer the lowest cost.
Moving into functional analysis, here you can see our FAST diagram with the task function to provide a seat for the user and primary basic functions to support the user's weight and to allow adjustability in terms of the height, the angle tilting back and forth, and rotation. You can also see our secondary supporting functions, especially one to maximize the comfort of the user.
The function component mapping matrix shows the functionalities of each of the parts of the chair. This matrix allows us to understand how possible redesigns can affect the functions of the product.
To serve different customer groups, we broke down our functions into different categories depending on whether or not the customer desired those functions. For our secondary customer group, they did not require premium functions. To serve the appropriate functions for the customer groups, different parts were required. These parts are listed in the table on this page.
Here you can see the primary and secondary customer group designs. All parts in the secondary customer group are reused from the primary group, and you can see the armrest, neck support, and wheeled base that are additional to the primary group. Here you can see the interface of the neck support to the backrest, and also a depiction of what the interface looks like without the neck support in the secondary customer group. Shown here is the interface between the armrest and the seat bottom, as well as what the interface looks like without the armrest in the secondary customer group product. Here you can see the interface between the caster wheel and the seat leg, as well as the secondary customer group variant, which uses a nub instead of a wheel. To facilitate delayed differentiation between our product family variants, assembly diagrams were created to identify how the process could be reworked to reduce the number of nodes in the diagram. Our improved assembly sequence is displayed on the bottom here.
Using this improved assembly sequence for delayed product differentiation, we looked at a manual assembly analysis looking at the handling and insertion time of each part. In total, it came to 817.62 seconds. An area of improvement we looked at on the platform of the chair was in the welding of the legs to the outer shell of the height adjusting piston. One improvement was to combine these into a single part with a central cylinder. Another area of improvement was to design the outer shell of the height adjusting piston to snap fit into the cylinder with an alignment feature. The assembly of the armrest module to the seat was also looked at for improvement. Design actions included combining the top and pole of the armrest into one part to reduce part count, as well as incorporating an alignment feature to the seat bottom and a chamfer to help with bolt alignment. In total, these savings bring the assembly time down to 6 minutes 27.42 seconds, with an assembly efficiency improvement from 6.97% to 14.71%.
For automated assembly improvements, the backrest was chosen as the target platform. Following the handling cost and insertion cost analysis, we can see that the backrest bottom and top operations have significant cost, and many more parts are being used than the theoretical part count, driving costs higher. The changes made were to universally thin the material, add ridges for support, in order to allow the part to be made from a single injection molded part, reducing the fastener count to 0. Also helping with this is to use a side pull to create a cavity feature that allows for easier alignment and insertion of the V connector. The interface between these two things was also changed to be chemical bonding from the original mechanical fastening. As shown in the final analysis, the cost was reduced by 55%, and now we are using the same number of parts as the theoretical part count, reducing the costs of unneeded parts.
For the base, we needed to collect a few parameters to determine which process should be used. The outer profile of the base is about 25 inches by 26 inches and with a height of 5.1 inches. The volume of the actual part is 55.78 cubic inches. The surface area of the part is 593.28 square inches, and this comes out to a mass of about 14.7 pounds. The process selection for the base was fairly straightforward. The batch size was the main constraint on the production of the part, and die casting was the obvious choice. The process selection for the armrest part was much more difficult. One of the things that we had to do was decide whether the part should be hollow or solid on the inside. The outer profile of this part would be 10¼ inches by 2 inches by 11.6 inches. Its volume would be 22.69 cubic inches. The surface area would be 208.63 square inches, and its mass would be about 0.877 pounds. The thickness we decided to go with, if it was hollow, would be 5 millimeters. Both injection molding and compression molding would be valid choices for this part, but we decided to go with injection molding because we are more familiar with the design process surrounding it and the cost structure of injection molding.
While process selection correctly suggests injection molding for the armrest, the design's shape itself isn't exactly tailored for the process. The most notable issue here is the fact that it encloses an angled cavity that makes retraction and internal mold access quite cumbersome. Manufactured as one single part, the flat rest is not actually possible to make, thus we must adjust accordingly. One option is to use design guidelines that tell us to avoid internal depressions. If we cut out the ends of the rest and the base of the leg, we can now eliminate core lifters and make manufacturing more feasible, but it still requires side pulls and now 3 end caps to be clicked into place after the fact. All this added manufacturing, assembly, and so forth isn't ideal. Therefore, we investigate a more holistic redesign. Here, we employ a new hollowed-out honeycomb design that can be injection molded axially and without any additional steps or parts. Draft angles on all sides, no sharp corners, and rib geometries designed to the specifications from lecture allow for much more enhanced manufacturing. We also change materials to the more affordable HDPE. Without side bowls, we can now use a triple cavity mold instead of a single one, and by organizing the arms in a staggered fashion, as shown in the green image below, we can be significantly more efficient about the mold area we use. When we run the numbers with the solid armrest design, just like the rolling pin example from lecture 14, the savings are evident. Material costs drop dramatically, operating cost remains roughly the same, and mold cost only increases due to the humongous number of core plate surfaces with the ribs, bumping XO, MX, and other cost factors. In the end, each individual part saves us over $1.10, with our total volume helping shave off $113,000.
The base legs were manufactured using die casting, and their redesign was done using the Design for Die Casting guidelines. One of these guidelines is to use a uniform wall thickness and we also reduce the wall thickness to 5 millimeters, assuming a finite element analysis allows it. Another thing we did was that we decreased the tolerance cost factor to plus minus 0.35 millimeters because the legs doesn't require such a precise tolerance. We could do that. And we also added draft angles to allow an easier pattern removal. In addition to the 3 modifications mentioned before, we also filleted some of the corners, as you can see in the bottom right image. We decreased the surface finish cost factor to have a medium quality because the legs doesn't require to have such a high quality value. And we kept the rib thickness to 80% of the wall thickness. Finally, the total cost per part was calculated for the original base legs and for the base legs after the redesign, and it was found out that for the total production volume, there will be savings of nearly $160,000.
Our design team has created the idea of a bulk rental service for our product, specifically targeted at things like large conferences and conventions where large numbers of seats are needed for a short time. This idea allows for large numbers of potential customers to try out our products without needing to make the full cost purchase. In conclusion, through this project, our team has reduced the numbers of parts and the assembly cost of the original design we started with, as well as created delayed differentiation between product family variants. While we think there are still potential further improvements that could be made, we are proud of the progress that we were able to make.